All right, so today we're going to be talking about now when we do either an experiment multiple times or if we are looking for multiple outcomes for an experiment. So today we're just going to focus on OR probability. This is when you do an experiment only one time, but you're looking for multiple outcomes, like a 2 or a 7, or a red or a blue. So when you do an experiment one time and are looking for multiple So you do an experiment one time and you're looking for multiple outcomes. So like rolling a die once. We want the probability of rolling a 2 or a 3. Because you're only doing the experiment one time, you're only going to get one number as your result, and you would be happy with a 2 or a 3 for that result. Okay, so OR is the key word there to let you know that you're only doing the experiment one time. So with this OR probability, there are two types of situations, two types of events that we could be dealing with. The first is mutually exclusive or disjoint events. This means that the two events you're looking for cannot happen at the same time. So like the 2 and the 3, if you roll a die one time, it's not possible to get a 2 and a 3 at the same time. So those would be mutually exclusive or disjoint events. Shh, guys, please stop talking. So mutually exclusive are when two events cannot happen at the same time. So that means if one happened, the other one didn't. If you rolled a 2, that automatically means you didn't roll a 3 because it can't happen at the same time. So rolling a 2 or 3 because you can't have both. So that's why it's mutually exclusive. Okay, then we have overlapping events, or sometimes called just not disjoint. Everything in probability has like multiple names, so it's fun. So overlapping or not disjoint events just means it is possible for those two events to happen at the same time. When two events share some outcomes, or they can happen at the same time. So this would be like rolling a 2 or an even number. So if we want to roll a 2 or an even number, 2 is even, and so it is possible to get both of those things at the same time. So 2 is in that overlap area where it satisfies both events. It's an outcome in both of them. So whenever we are dealing with this OR probability, we're doing our experiment one time, and we're looking for multiple events or multiple outcomes, then we use the addition rule. So whenever we have the word OR, we're always going to be adding. So OR means addition. So we want to calculate the probability of event A or B. Then we will just take the probability of A plus, because it's the addition rule, the probability of B. But then with this OR probability, since there is the chance that we could have overlapping events, if we just left it at this, we would be double counting events if there is that overlap. So if we were talking about rolling a 2 or an even number, we would count 2 twice with the 2 probability and with the even number probability, even though there's only 1 2 on a die. So in order to eliminate any double counting issues, we then have to subtract that overlap, the probability of A and B happening at the same time. So we're just subtracting the overlap to make sure we don't double count anything. Okay, so example 1, consider we're rolling a fair die. Fair die just means it's a normal die, 1 through 6. The event E is rolling an even number, and the event F is rolling a number less than 5. Compute the probability of E or F. So it's helpful now if we get into the habit of making some notes kind of when we're given a problem like this. So we have the probability of E or F, so or means we're going to be adding. And then we have some events that are just defined, so it'll be helpful if we list out the possible outcomes. So rolling an even number, that would be either 2, 4, or 6. And then F is rolling a number less than 5, which would be 1, 2, 3, and 4. So whenever we have OR probability, we always have to check to see if there's any overlap. So in between those two events, E and F, are there any outcomes that are in both? Is there any overlap? Yes, there's 2 of them. 2 is in both and 4 is in both. So do we have overlap? Yes. And so since there's overlap, that means they're overlapping events. Pretty straightforward there. And the overlap is 2 and 4 are in both. Okay, so it's good to kind of know all of this information before we start trying to plug stuff into that addition rule there. So now we want to calculate the probability of E or F. So we're going to take our probability of E plus the probability of F minus the probability of E and F, or that overlap. So now each of these separate things is just like the probability that we were doing last week. So just one at a time. The probability of E, the probability of rolling an even number, would be 3, because we have 3 possible outcomes, over 6, over the 6 possible when you roll a die. And then plus the probability of event F, which is rolling a number less than 5. We have 1, 2, 3, 4 outcomes in that event over the 6 possible. But if we just left it at that, we counted the 2 and 4 in both of them, so we double counted those. So we have to subtract the overlap, and we have 1, 2 outcomes in that overlap, so it would be minus 2 over 6. Oops. Okay, so then we just do this addition and subtraction. So adding and subtracting fractions, the denominator stays the same. 3 plus 4 is 7, minus 2 is 5. All right, any questions? All right. So moving on. Example 2a, so suppose a single card is selected from a standard deck of 52 cards. Compute the probability of event E, drawing a king, or event H, drawing a diamond. So if we look at event E, drawing a king, how many kings are there in a deck of cards? 4. So we have the king of hearts, we have the king of diamonds, we have the king of clubs, and we have the king of spades. My artwork is impeccable. Don't be jealous. Okay, you don't always have to write out all of them. I'm just doing it for the purposes of the notes so you can kind of see. Once you start doing more and more problems, you'll be able to do this in your head, or you could just write 4 outcomes just so you know how many. And then drawing a diamond. How many diamonds do we have to choose from? 13. Yeah, there's 13 of each suit. So here I'm just going to write out 13 outcomes. I'm not going to write out all 13 cards. But then we do have this word or here, which means addition. And that means we have to check for overlap. So are there any cards in a deck of cards that are both a king and a diamond? Yes, there's one, the king of diamonds. So yes, we have the king of diamonds. So when we do our probability of the probability of king plus the probability of a diamond minus that overlap. So minus the probability that you actually get the king of diamonds, because we don't want to double count. So the probability of drawing a king would be 4 over 52, because we have 4 kings, plus the probability of a diamond, which is 13 over 52, and minus the overlap. There is one outcome in the overlap, that king of diamonds, so we'd minus 1 over 52. And we do that addition, and we should get 16 over 52. All right, do you guys have any questions? Could you try B and example 3? So go ahead and try those two, B and example 3. All right, guys, so for part B, we have the probability of drawing a face card or a club, so that or means addition. It means we're going to be adding. We have to use our addition rule, so we have to check for overlap. So in between being a face card and a club, there are 3 outcomes that overlap, the jack, queen, and king of clubs. So when we do our addition, there are 12 face cards, so 12 over 52, plus there are 13 of each suit, so plus 13 over 52. And then there are those 3 outcomes in the overlap, so we would minus 3 over 52. So that should give you 22 over 52. Are we good there with letter B? Yes? Cool. Okay, and then example 3. We roll 1 die. What's the probability of getting a 1 or an even number? So again, we have that or there, which means addition. I'm emphasizing this because tomorrow we're going to learn when we're going to multiply probability, and so you have to kind of get used to identifying when you're going to add and when you're going to multiply. So it's a good habit to get into now. Whenever you see the word or, put a little plus sign so you know you're adding. And so getting a 1 or an even number, if there's any overlap, is it possible to roll a die and get a number that's both a 1 and even? Nope, because 1 is not even. So since there's no overlap, that means these are disjoint events or mutually exclusive, because they cannot happen at the same time. You can't roll a 1 and an even at the same time. And so when we do our addition rule, the probability of getting a 1 is 1 over 6. Adding the probability of getting an even number, which is 3 over 6. But then since there's no overlap, you would essentially be subtracting 0, which isn't going to change anything. If you want to write it, that's cool, but you don't have to. You would just add these and you would get 4 over 6 for the probability. Okay? So for problems like these, when I'm giving you describing different events, and you can just set up the fraction right as is to do the probabilities, you can just use the rule, the addition rule. It's pretty straightforward. Just do one probability at a time. Make sure you always double check for overlap. Example 4. We have, now it's set up a little bit differently. Instead of describing the experiment to you and you having to calculate the probabilities are given to you. So in a certain town, 0.6 of the households own a cell phone, 0.4 own a pager, because this is still relevant, and 0.2 own both a cell phone and a pager. The proportion of households that own a cell phone but not a pager is what? So really, if we set up the addition rule with this situation here, we'd have the probability of a phone or a pager oh wait, just kidding, that's not gonna work. So I'm sorry, just keeping you on your toes, making sure your erasers work. So when we have this and we want to find the probability of just one and not the other, so not including the overlap when I'm not giving you the individual outcomes, like for rolling a die, you know all the individual outcomes. This is where Venn diagrams can come in handy. You don't always have to use them, but for these problems it's really kind of the one that makes the most sense. So if we have a Venn diagram here, we'll have a cell phone circle and a pager circle. And so in the middle, where the overlap is, it says 0.2 own both, so 0.2 is in the middle. Guys. Are you good? Can I go? Yeah. Thanks. Okay, and then we have, for each individual one, so we have 0.6 own a cell phone, which means this entire circle has to add up to 0.6. That 0.2 is included. So how could we figure out what number goes here? How many just have the cell phone? Yeah, if we know something plus 0.2 has to equal 0.6, if you just subtract 0.2, that'll give you 0.4. Have just a cell phone, and you can do the same thing for the pager, where it says 0.4 own a pager. So we'd have something plus 0.2 has to equal 0.4. If you do the subtraction, it'll give you 0.2. Okay, so Venn diagrams are helpful when it's these types of questions, the one but not the other type of question. If it's just the or probability or the overlap stuff that you're dealing with, then you can use the addition rule that we used. Okay. You guys have any questions? Okay.
I'm so lost.
Okay. So are you good with the fact that we have two circles for our Venn diagram?
Yeah, I know they're there.
So we have houses that have pagers, we have houses that have cell phones, we have some that have both.
Right.
Okay. So this circle is representing all the houses that have cell phones.
Mm-hmm.
That circle is representing all the houses that have pagers. Where they overlap, these are the houses that have both.
Okay.
So you got to start from the inside and work your way out. So it says right here that 0.2 own both. That's why we put 0.2 in the middle. And then for a cell phone, that's 0.6, meaning this whole cell phone circle has to add up to 0.6. And we already have the 0.2 in the middle. So the leftover is the only cell phone people, which is 0.4. And then same idea for the pager. So to answer the question, the proportion of households that own a cell phone but not a pager would be the number in just the cell phone part, not in the overlap. So 0.4. Oops.
Or just the ones that
No, just, what do you mean the other problems? Not really. This is really just for when you're trying to find the one but not the other type of question, where it's cell phone but not pager. Yep.
Thank you.
Yes. All right, so the oh, we're not done yet, just kidding. Faked you out. One last thing we got to talk about is called the complement of an event. So whenever you see the word complement, you need to think the word not. The complement of an event is everything that's not in that event. So if we have a sample space S of a probability experiment and E is an event, the complement of E, and we use this notation, E with a little c kind of in the exponent. It's the complement of event E. Which also means not E. All the events that are not in E. So if we had a sample space, those are numbers 1 through 10, and the event E was the odd numbers, we would just list our odd numbers like we were doing earlier. So 1, 3, 5, 7, 9. So then the complement of E, which is written as, again, that E with the C, superscript. The complement of E would be all the outcomes not in E. So in that event E, we have just the odd numbers. So the outcomes that are not in E would be the even numbers. So the complement of E should be just the evens. 2, 4, 6, 8, 10. Okay, so the event is just as normal, however we defined events before, and then the complement of E is just everything else, everything that's not in that event that we're talking about. And so since between the event and the complement of the event, we have the entire sample space, right? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have all of the outcomes in the sample space included in an event and its complement. If we take the probability of an event plus the probability of the complement of that event, it will equal 1, because that has all of the outcomes included in both of those, and there's no overlap, because what's in the event cannot be in the complement. Okay, so this is a helpful thing to know, that if you know the probability of an event and you want to find the probability of its complement, you just have to subtract it from 1. So to see that in action, example 5, according to the National Gambling Impact Study Commission, 0.52 of Americans have played state lotteries. What is the probability that a randomly selected American has not played the state lottery? And again, it says not playing the state lottery is the complement of playing the state lottery. So if we take the probability of playing the lottery plus the probability of not playing, which is the complement, that should equal 1. And so they told us what the probability of an American playing the lottery is. It's the 0.52. So then to just solve for that probability, you would just take 1 and subtract 0.52 from both sides. So that means the probability of not playing the lottery would equal 0.48. Okay, so you really don't have to write out when you're doing problems, you don't have to write out all of that work. You can just go right to the subtraction, and that's fine. This is just so you can see why that works. All right, so for the self-assessment, you don't have to do the first one. Don't worry about the Venn diagram. It's not helpful for that problem. So just go ahead and do number 2, calculate the probability of E or F. Then I'll check it, give you the homework, and